As you can see, today's topic is ice tables. Now you might be wondering what's an ice table. Well, you might be surprised to learn that an ice table has nothing to do with ice or tables, at least not the kind you eat at. With an ice table, it's more like the little chart that we fill in, but we're going to use it to fill in information on initial concentrations, changing in concentrations, and equilibrium concentrations. And if you look, that's where we get the ice from. Okay. And we're going to use that to figure out stuff about equilibrium. So we're going to use it to figure out perhaps the value of K, if we're not given K, or we're going to use it to figure out concentrations of things at equilibrium. All right, so what is it going to look like? It's going to look like a chart, but the kind of question is going to look like this. You're going to be given a system at equilibrium. You're going to be told perhaps initial concentrations, because remember how we study equilibrium. We put things into a container and we let them react. So we know what we start with, and then we have a way to figure out what we have at equilibrium. So we'll know the concentration of something at equilibrium and the things that we started with. And then we may or may not know a value of K. Okay? So we'll do a couple of examples of each, or at least one of each. So you've had time to read this, you've had perhaps pause it to write it down, but what we've got here is we have known initial concentrations and known equilibrium concentration. And then your job is to calculate the other values, the other concentration equilibriums, other equilibrium concentrations, and the value of K. Okay, and you're going to do that using an ice table. Now an ice table is going to be a really, really handy tool. We'll shorten it up a little bit later, but it's really important. So this is what the table actually looks like. We put in the columns the things involved in the reaction, so our two reactants and our one product in this case. Normally I like to put a little arrow, write it as a reaction equation. It just didn't really fit very well the way I was trying to do it here. And then the three rows. Initial concentration, change in concentration, and equilibrium concentration. Initial concentrations are fairly simple and straightforward. Now, I wasn't told the zero. Well, okay, it's educated guess time. You start with reactants hoping to make products. So you don't start out with products, although it's possible you could as a study of equilibrium. Now, how is this thing going to change? Well, here's where we need the balanced chemical equation. In the balanced chemical equation, the reaction said that 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia, NH3. So what's going to happen is, as that reaction progresses, the reactants are going to decrease. So they're a minus, and they're going to decrease following the balanced chemical equation. So every time 1 nitrogen reacts, 3 hydrogens will react, and they will increase the ammonia, the product, by 2. Well, I don't know how many are going to react. I don't know if it's going to be 1 nitrogen or 12 nitrogen, so we'll call it X nitrogen. So X number of nitrogens are going to react. 3 times as many hydrogens will react, and they will produce 2 times the number of ammonias. So what do I have at equilibrium? Well, at equilibrium I have where I started with the change. So 0.5 minus the x, 0.8 minus the 3x, and the 0 plus the 2x. I'm just adding up the first 2 rows. Now what do? Well, now I solve for x. Oh wait, there's one more piece of information that I needed to know, or that I was given actually. Not only do I have this in terms of x, but I was also told in the question, check back, that at equilibrium the concentration of ammonia was 0.3. That means 2x equals 0.3. All right, solve that for x. X is 0.15. Now I know what x is. I can substitute x in for all those other. This is a lot like math. So substitute my known value in for x, and I can calculate the other concentrations. And there we have it. Now from here, well, I have everything I need to know to solve for K. Except one thing. I need to have not only my equilibrium concentrations, which I just solved for, but I also need to know my equilibrium expression. Oh, that's products on top, reactants on the bottom, the balancing numbers become the exponents. Substitute my known equilibrium concentrations in, so now I'm calculating the equilibrium constant, so I need equilibrium concentrations, and more math. And of course, as you know, we don't really worry about the units on K. K does have units, but we don't worry about them because the units aren't as helpful as the number. Okay, what about doing something else with an ice table? So we have another situation here where we have a system at equilibrium and we're given something about the equilibrium concentration, and now we're also told, instead of, I said equilibrium concentration, we're told starting concentrations. We're not told equilibrium concentration, but we are told K, so we know how the products and reactants relate to each other at equilibrium. Make an ice table. It's going to be our thing. All right, the ice table is going to look the same. Reactants to products, following the balanced chemical equation. Again, I used make it a balanced chemical equation and then put my columns below that. My initial concentrations were given. I wasn't told anything about the products, so probably didn't have any. My change in concentration, well, the reactants are going to go down, the product is going to go up. That's how reactions work. And then at equilibrium, what I start with the change. Now, last time I was told one of the equilibrium concentrations. I'm not told that this time. So what do I have? Well, what I have is an expression in X, and if I substitute that into the equilibrium expression, it looks like that. So I have stuff I can work with. Now, you might be looking at that and thinking, oh man, that is going to be some kind of ugly. It could be, but if you look at what we've got right here, we can actually take a shortcut. Nah, not a shortcut. We can do smart math instead of long math. At this point, if I take the square root of both sides, perfect square on the left, okay, not a perfect square on the right, but I can take the square root of the left and I can take a square root of the right, I end up with a simplified expression. Now, not quite so ugly. And now I'm just solve for X as I would solve for X in a, like a grade 10 kind of problem. Once I solve for X, I know what X is. Phew, I'm done. No, you're not, because that you'd be done in math. This is chemistry. We have to do something with that X. We have to use that X to solve for the equilibrium concentrations. So I know what X is. I also know each thing in terms of X. And luckily, some of them are the same. Oops, back that up just a little bit. I keep doing that. So there's my equilibrium concentrations. Okay, question that pops up in my mind, perhaps yours as well, is, okay, it worked for that one, but what about a reaction that it wouldn't work so well? So you don't need to write this down, but here's a reaction where if I had initial concentrations that looked like this, and the change to the equilibrium concentration is going to look like that. Okay, yeah, the ice table is the same. I'm doing the same thing. If I then were to put that into the equilibrium expression and I knew the value of K, if I went to solve that thing, you'll notice that now we're back to some kind of ugly. At this point, we're going to stop. But for other questions where we get to that ugly point, we might have something else we can do because it's chemistry or because something else that we know about the equilibrium. But for right now, let's not worry about cases where things get nutty. Let's worry about things where we know what's going on. That's all there is to an ice table. As you know, it's putting the information in. I'll tell you where some people get stuck is when to make it plus, when to make it minus, and things like that. It's really simple. Is the concentration going to go up? Plus. Is the concentration going to go down? Minus. As the system is getting to equilibrium. And then they'll sometimes get stuck on that last line, the E line, because all that is where I started, initial, and how did it change? Combine that. So it might be 0.2 plus X, it might be 0.2 minus X, depending on whether it's a reactant or a product. That's all there is to it. We'll talk to you in class, and we'll do lots of ice tables, don't worry.